You ever sit down and think to yourself, I wonder if I could use the principles of quantum entanglement to measure Earth's rotation? Well, researchers at the University of Vienna did just that and uncovered some crazy results. Let's get into it. On June 14th, a research paper was published that described how for the first time ever, the principles of quantum mechanics were used to precisely measure the rotation of Earth. Now, I understand that research papers are pretty dense and tough to get through, so I'm going to explain all the basics and break down what the researchers did and what they discovered in a more engaging and understandable way. Alright, let's first break down all these intimidating words. What even is this so-called quantum entanglement, and what does it have to do with measuring Earth's rotation? Well, imagine you have two magical dice. Every time you roll them, they land on the same number. For example, you roll a 6 on one, the other one instantly shows 6 too, even if they're on different sides of the world. This is what quantum entanglement is like. But instead of two dice, we're talking about these tiny particles called photons. Alright, now before you start yelling at me, hey, what the heck is a photon? Let's take a moment to appreciate how crazy this concept is. We have these two dice that are like they're communicating with each other. They land on the same number every time. Now, on the macro scale in our everyday lives, that might seem like crazy and that it's magic, but the quantum world has different plans for us. So, what is a photon? At their core, a photon is the smallest unit of light. Just like how a molecule is the smallest unit of water that still shares all the properties of water, a photon is the smallest unit of light that still shares all the same properties of light. Of course, we can get into the details about how a photon can act as both a particle and a wave, but we'll save that for another video. For now, let's just keep those properties in the back of our mind. Now that we got all those daunting terms out the way, let's switch back to Earth's rotation. We know that Earth spins on an axis, just like how a basketball can spin on your finger. But how can we measure this spin in a very precise way? Introducing quantum entanglement. So here's the cool part. Scientists have found a way to use these entangled photons to measure the rotation of the Earth using this crazy device called an interferometer. Now, I know I said I'm done with all these daunting terms, but this is the last one, I promise. So an interferometer is a scientific instrument that splits a beam of light into two different paths, sends them in different directions, and then finally recombines them through a detector. Now, for specific quantum experiments, there's some slight adjustments that have to be made. But here's how it works. First, a laser generates a beam of light. This light then passes through a special crystal that creates entangled pairs of photons. These entangled photon pairs are still part of their original laser beam, but we're just going to focus on one of these pairs to make it easier to understand. Next, the beam of entangled photons are split into two identical beams with a beam splitter. This beam splitter acts as a two-way mirror, sending one half of the light in one direction and the other half of the light in another. Now here's where it all boils down. Due to Earth's rotation, one beam or one of the entangled photons will complete its path faster than the other entangled photon or the other beam. This effect is called the Sagnac effect, and it's the basis of this whole entire experiment. Think of this like two identical ladybugs that are running around a spinning disk, except they're going in opposite directions. The time it takes for this ladybug to complete its path depends on the direction it's running. If it's going in the same direction as the spin of the disk, then of course it's going to complete its path faster. Now let's switch gears and go back to the experiments. So after these two entangled photons complete their respective paths, they're going to pass through the detector, and this is where they're going to interfere with each other. So what's crucial here is this concept called a phase shift. If the Earth was not rotating, then the two entangled photons or the two beams would recombine perfectly. But because the Earth is spinning, the time it takes for the photons to complete their path is going to differ, and this is going to cause a phase shift when they recombine. The waves do not overlap perfectly, so this is going to cause a change in their so-called interference pattern. Now, using mathematical formulas and equations, scientists can look at how these weird interference patterns change over time, and from that, measure the rotation of the Earth to a very precise degree. So here's where the entanglement of the photons come into play in this experiment. So first off, entangled photons are very sensitive to changes in their surroundings. This means that any tiny difference in the paths traveled by the photons due to Earth's rotation will result in a noticeable effect in their combined states when the two photons recombined when they pass through the detector. Well, this makes it possible to detect even the smallest phase shifts. Also, because these entangled photons are linked to each other, they can help filter out any noise or fluctuations that could potentially interfere with our data and make the measurements less precise. Okay, what's the big deal of this experiment, and why is it significant? Well, understanding and measuring Earth's rotation to such precision can help us in many areas, from improving GPS systems to exploring and understanding geophysical activities, and even researching and testing more theories, such as in quantum gravity. It's just really a groundbreaking way of observing our planet using the crazy and spooky effects of quantum physics. Well, that's it for this video, and I hope you enjoyed our exploration into the quantum world and into Earth's rotation and how they can interact with each other. If you learned something new, please hit the like button, subscribe for more amazing physics explanations, and also drop a comment if you have any questions or any topics you want me to cover next. Till next time.